All right, let's dive into something that's literally the foundation of how everything moves. Newton's three laws of motion. And look, these aren't just dusty rules in a textbook. They explain absolutely everything, from a planet going around a star to something way more familiar. Yep, we're going to make this all make sense by focusing on one simple thing we've all done, trying to push a heavy box across the floor. It seems so basic, right? But trust me, every single part of that struggle is a perfect window into the genius of Isaac Newton. Okay, so picture it. You walk up to this box, it's just sitting there, you give it a little nudge, and what happens? Yeah, nothing. It just resists. Well, that stubbornness actually has a name, and it's the key to Newton's very first law, inertia. So what exactly is inertia? You can think of it as an object's deep desire to just keep doing whatever it's already doing. And here's the most important part. An object's mass is how you measure its inertia. The more mass something has, the more stubborn, the more inertia it has. Our heavy box doesn't want to move simply because it's got a lot of mass. This is part one of the law. Our box is at rest, and honestly, it's perfectly happy that way. To get it to do anything else, you have to come along with an outside force that's strong enough to overcome that laziness, its inertia. Until you do that, it is not going anywhere. And here's the flip side of that coin. Imagine you were an astronaut in space. No friction, no air. And you gave that same box a push. It would just keep on gliding in a perfectly straight line, at the same speed, basically forever. The only reason that doesn't happen here on Earth is because of all those invisible forces like friction and air resistance that are always working to slow things down. Okay, so we know the box is stubborn, it has inertia. So how do we actually win? How do we get the thing to move? Well, that brings us to what might be the most famous equation in all of physics, Newton's second law. You've all seen it. F equals ma. Force equals mass times acceleration. Put simply, the harder you push it, the more force you apply, the faster it will speed up, or accelerate. But you see that m for mass right in the middle? That's the inertia. It's always there, working against your force, making it harder to get the object to accelerate. Just think about it this way. You give the exact same shove to two different boxes. One is full of bricks, the other is full of feathers. The light feather box just zips across the room. It has very little mass, so it's easy to accelerate. The heavy brick box, well, it barely moves. You used the exact same force, but the mass completely dictated the result. Now let's talk about the third piece of this puzzle. As you're pushing on that heavy box, really leaning into it, you feel something, don't you? You feel the box pressing back against your hands. That is not in your head. That is Newton's third law, happening in real time. Now, this is probably the most famous of all of Newton's laws, but it's also the one that trips people up the most. All it really means is that forces never exist alone. They always come in pairs. You can't just have a push, you always get a push back. So let's look at this pair of forces. The first one is the action. That's you pushing on the box. Your force is being applied to the box. Pretty straightforward, right? But at the very same instant, there's the reaction. The box applies a force that is equal in strength and in the opposite direction, back onto you. Back onto your hands. That pressure you feel, that is the reaction force. Okay, and here it is, the classic question, and it's a great one. If you push the box with, say, 50 newtons of force, and it pushes you back with 50 newtons of force, shouldn't that just be a tie? Shouldn't they cancel each other out so that nothing goes anywhere? And here is the secret, the aha moment. The reason they don't cancel out is because they are acting on different objects. Your push acts on the box. The box's push acts on you. To cancel out, forces have to be acting on the very same object. This little detail is the key, and it's the reason why things can move at all. All right, so you've done it. You push the box, it's sliding along, and then you stop pushing. Now, according to the first law, an object in motion should stay in motion. But it doesn't, does it? It grinds to a stop. So what's going on? Well, we have to talk about one last invisible force that's always in play: friction. Now, friction isn't just one thing. When the box is just sitting there, you're fighting against static friction. You can think of it like a temporary glue holding the box to the floor. But once you finally break that glue and get the box sliding, you're now fighting against kinetic friction, which is just the resistance from the surfaces rubbing together. And you have totally felt this, I guarantee it. That first big push to get a heavy piece of furniture moving is always the hardest part. Once it's actually sliding, it's still tough, but it's noticeably easier to keep it going. So why is that? Well, it's because that stuck force, the static friction, is almost always stronger than the sliding force, the kinetic friction. So for example, maybe you need 40 newtons of force just to break that initial static grip. But once it's sliding, you might only need 30 newtons to keep it going. That 10 newton difference is exactly what you feel. Okay, so we have all the pieces on the board now. Let's do a quick recap and see how this all comes together to tell the complete story of pushing that box, from start to finish. And here's the play-by-play. First, you have to apply a force strong enough to overcome the box's inertia. That's law number 1. And to break the grip of static friction. As you push, that force causes the mass to accelerate, just like F equals ma says. That's law 2. The whole time, you feel the box pushing back on you. That's law 3. And you have to keep pushing to fight the kinetic friction to keep it sliding. It's like a perfectly choreographed dance of physics. And that's what is so amazing. We've just been talking about moving a simple box. But these exact same rules, these are the principles that launch a rocket into orbit, that keep the Earth circling the sun, that even describe how entire galaxies collide. It's 3 simple rules for the entire universe. So the next time you're in a car that brakes hard and you feel yourself lurch forward, you'll know, hey, that's my inertia. You'll start to see these forces everywhere. The whole world is basically one big physics lab, and now you have the instruction manual. So think about it. What motion around you is going to make more sense now?